I've been working with my team in titanium technologies these past 5 years because New Zealand has quite a thriving and developing titanium industry at this moment, and we see it as our role to support and encourage those industry partners and players wherever we can. After my PhD graduation, which had been in the area of glass science and technology, I went and worked in the UK with Pilkington Brothers, a big glass manufacturing company, and learned a lot in the context of that about technology transfer. And for me, that was a really telling experience, and one where I learned a lot about how important applied science can be in developing economies. So we started to do work around the mid to late 80s on some of these advanced ceramics. Its main theme was to develop these sail-on materials into a commercial opportunity for New Zealand businesses. These are amazingly strong materials, so they cope with thermal shock, they cope with mechanical stress, they cope with thermal stress, and they're extremely tough materials. So this is a thermocouple protection tube. So if your business is processing molten aluminium, you need to measure the temperature of that molten aluminium, and you want to put a thermocouple into the mix to keep the temperature constant. You can't put a thermocouple into molten aluminium. What you do is you put it into the sleeve, and then you put this metal resistant sleeve into the molten metal. These last a long, long time. They're a high performance ceramic. They cope with the thermal shock of the molten aluminium. They give very good heat transfer through the walls to the thermocouple, and this is a great New Zealand commodity export, goes all around the world. We've been working for many years in the advanced ceramics area, basically working with ceramic powders and converting those ceramic powders through various processing steps into ceramic bodies of quite complex shapes, working in controlled atmospheres, and really when you get down to it, that's the sort of stuff we have to do with titanium powders as well. So there was a really obvious sort of transfer opportunity from the ceramic technologies to the titanium technologies, and that's kind of where it all started. Titanium is one of those materials that it's used all over the world internationally, and airplanes are made out of it, and a lot of other rather exotic and exciting things, because titanium is a really light, strong, amazingly durable material. But in fact, it's an incredibly wasteful material to use, and it's really a challenge to recycle that material. If you take powder materials, you can develop processes that make near net shaped bodies, and then all you've got to do is kind of dress the end result with minimal wastage and minimal loss. And what I'm showing you here is a jawbone for a dog that has been 3D printed in titanium alloy powder. Obviously you can see there's a porous structure in the middle of that, and what we're wanting to do is help improve that pore structure, because the important thing for medical implants is that the pore structure you set up has to be able to accommodate blood vessel ingrowth and tissue ingrowth. I guess that's been a theme of all of my work through my whole working career, using materials science to benefit New Zealand in one way or another, whether it's been in the context of cement technologies for geothermal wells, or specialist hydrogen filters using nanotechnology, or advanced ceramics, or more recently in titanium technologies. The idea that materials science can underpin technologies of great benefit to New Zealand is really important to me, because I see real opportunities and benefit for New Zealand.